Hello, today we're continuing with our GCSE Physics revision series looking at the gas laws. So the whole of this video relates entirely to gas. We're going to have a gas usually in a container so that we can contain it. And if we think about what is actually happening inside that container, we've got molecules of gas. Those molecules have virtually no intermolecular forces, because that is the definition of a gas, that the molecular forces which would hold solids and liquids together have largely been broken, and so we've now got molecules which are essentially free to move about as they like. As they move about, they are going to collide with other molecules, so they're going to exchange energy, and some of them are going to be moving fast, some of them are going to be moving slow, and they're going to be moving in all directions, and they're going to have different velocities. What we do know is that if we add heat to that container, that is the equivalent of adding energy to that container, and that will cause the temperature to rise because we're not changing state. So adding heat means temperature rises. And that effectively means you're adding kinetic energy, which means on average that the velocity of these molecules is going to increase. So although we don't know what's happening to each individual molecule, we do know that on average, the average velocity, which I've called V bar, is going to increase as the temperature increases. The reason, of course, is that heat is energy. Energy in the form of kinetic energy is half mv squared. So if the energy increases, then the velocity increases. And in this case, we're talking about the average velocity of all of those molecules. Each of those molecules will have a mass. And it will also have a velocity. And as we've said, they won't all have the same velocity. There will be a distribution of velocities. But any given molecule will have a mass and it will have a velocity. And therefore it will have a momentum. And we've come across this before when we did our mechanics courses. The momentum is equal to the mass times the velocity. So every molecule will have a momentum which will be determined by its mass and its velocity. And as these molecules bash into one another, they're constantly exchanging momentum. Momentum is always conserved, but it may be being transferred between molecules. And that's why the molecule's speed is changing, because its momentum is changing. But every now and again, those molecules will bash not against another molecule, but against the surface of the container. So here comes my molecule, mass m, velocity v, and therefore momentum mv. It hits the wall and it bounces back. Let's say it bounces back with mv. There will therefore be a change in momentum, because remember, momentum is a vector. Initially the momentum was in the direction towards the wall, now it's moving away from the wall. There will be a change in momentum, which we represent by what we call delta p. That is a Greek letter delta. Delta p simply means there's a change in momentum. We don't need to worry too much at this stage what that change is. But there's clearly going to be a change because the direction has changed. And in our series on mechanics, we learnt that force is equal to the change in momentum divided by the time. So if you've got this box, which I'll just draw in 2 dimensions, and you've got, let's say, a molecule which hits this wall, then it hits this wall, then it hits this wall, then it hits this wall. In the time it takes between hitting the wall at this point and hitting the wall at this point, that is the time that you put into this formula. So there's a change in momentum, and that change in momentum happens every t seconds, which is the time it takes to come back and hit the wall again. And that will be a force on that wall. Now all of the molecules are moving about, so all the molecules at some point are hitting that wall. So all those molecules will have a combined force acting on the wall. Not just the force of one molecule, but the force of all the molecules hitting the wall. And I defined, when we did hydraulics, you may remember I defined pressure as force divided by area. This wall, if I now redraw it in 3 dimensions, this wall will have an area, area A. So the pressure on that wall will equal the total force of all the molecules divided by the area. And that's why a container of gas has pressure. It has pressure because the molecules are hitting the sides of the container. They are therefore changing momentum. The rate of change of momentum is the force. The total force of all the molecules hitting the side of the container divided by the area is equal to the pressure. So if we now think about our container, that container will have a certain volume, which we call V, and we can measure the pressure inside by using a pressure meter. That will give us the pressure P. For example, a pressure meter is often attached to the foot pump that you might use to pump up your car tyre. The pressure meter will tell you what the pressure of the air is inside the tyre. So we could measure the pressure inside this container with something like a pressure meter, and we know the volume. One way of doing it would be to fill the container with water and then empty it into a measuring jug, and that would tell you what the volume was. So we've got the pressure of the gas and we know what the volume of the gas is. And the first thing I'm going to do is take that container, and the volume of course cannot change because it's a fixed volume and we're measuring the pressure. And I'm going to put that container into what's called a heat bath. That could be, for example, filled with water. The point about a heat bath is it's so big that whatever the temperature of the bath, that will also be the temperature of the gas inside the container. And we can change the temperature of the heat bath simply by heating it up with a heating element. So the experiment we're going to do is we're going to change the temperature of the water. We might start at 20 degrees Celsius, then go up to 25, then go to 30, 35, 40 and so on. And every time we change the temperature, we're going to measure the associated pressure, and then we're going to plot that on a graph. Pressure against temperature. And what we find is that as the temperature increases, so does the pressure. And the points you will get on your graph look something like this. As the temperature increases, you find the pressure increases. So we could draw the line that joins up all those points, and that would be our pressure temperature graph. But what is interesting is if you back project. So if you just continue this line right the way back until you cross the line here, this point here is very interesting. This comes out at a temperature of minus 273 degrees centigrade. But what does it mean? Well, look what's happened on the pressure chart. The pressure has reduced. As the temperature decreases, the pressure decreases. Well, that's perfectly fine. What we found was as the temperature increased, the pressure increased, so it should work the other way around. As the temperature reduces, the pressure reduces. But look, when we get to this point here, the pressure is 0. Now, if the pressure is 0, that means that the molecules are not exerting any force on the sides of the container, because pressure is force over area. And if they're not exerting any force, that means there's no change in momentum. And if there's no change in momentum, that means the molecules are not moving. They are now absolutely stationary. And this is the lowest state of energy that the system can be in. You've taken so much energy out, you've taken so much heat out of the system that the molecules are now stationary. And you cannot get less movement than that. So you cannot go lower in temperature than that. And so this is called, as we've referred to it in a previous video, as absolute zero. And we call that 0 Kelvin. Not, as I said before, not 0 degrees Kelvin. When you talk about the Kelvin scale, then you simply call it 0 Kelvin. I remind you that 1 division on the centigrade scale is equal to 1 division on the Kelvin scale, but they are apart by 273. So 0 Kelvin is equal to minus 273 degrees Celsius or centigrade, and 0 degrees centigrade is equal to plus 273 Kelvin. But this straight line between pressure and temperature indicates that there is a direct proportionality between pressure and temperature, and that enables you to say that P1 over T1 equals P2 over T2. So what that means is if you have the heat bath at temperature T1 and you measure the pressure P1, and then you change the temperature of the heat bath to T2 and measure the pressure P2, then you will find that the value of the pressure divided by the temperature for the first temperature you did would be equal to the same. It would be P2 over T2 for the second temperature. But all of this assumes, of course, that the volume is constant, which it was because we put it into a fixed container where the volume couldn't change. And that is called the pressure law. Incidentally, the temperature is measured on the Kelvin scale, not the centigrade scale. The second experiment I'm going to do is going to be also conducted in a heat bath, but where the temperature doesn't change. So on this occasion, the temperature is going to remain constant. And I'm going to put my container in the bath, but I'm going to have a piston which can move up and down. The whole point about a piston is it doesn't let the air out, but the air can push the piston up or down. And the whole thing is going to be, let's just raise the sides a bit, the whole thing is going to be in this bath at constant temperature. So the temperature of the gas inside is not going to change. But what I am going to do is to put a heavy weight on the piston. That heavy weight will have a mass, let's call it mass M. If it has a mass, it will have a force, which is mg. So there will be a force acting down, mg. That's the weight of the mass. And that piston will have an area. So if you have the force over an area, that of course is pressure. So that mass has a weight. The weight acting over an area produces a pressure. That pressure is going down. The gas, of course, also has a pressure, which is acting up. And when the two pressures are the same, the piston will not move. So consequently, you put a weight on the piston, you wait until the piston doesn't move anymore, and then you know that the pressure of the air inside the container must equal the pressure that arises from the weight that's on top of the piston, which is given by mg over A. So you know what the pressure is. So essentially this is a means of measuring pressure against the volume of the gas. You would have maybe little marks up the side of the container to tell you what the respective volumes were. The temperature is remaining constant. What you do is you just put different masses on top of the piston, and that will give you different pressures, and it will also give you an associated different volume. And now if you measure, since the temperature is constant, what we're actually now going to plot is pressure against volume. And that's not very helpful. What you get is a graph that looks like that. And what that tells you is that as the pressure increases, the volume decreases. Right? So when the pressure is high, the volume is low. When the pressure is low, the volume is high. So when you have a very high pressure on here, hardly surprisingly, it pushes the gas in and the volume contracts. If you have a low pressure, the volume increases and the whole of the piston moves up. So high pressure is low volume, high volume is low pressure. The trouble is, it isn't a straight line. But you can make it a straight line by plotting, instead of pressure against volume, you plot pressure against 1 over volume. So if you simply take the inverse of the volume, then what you will find is the points once again form a line, and it's a straight line. And from this you can develop a formula that says that P1 V1 equals P2 V2. So if you start your experiment with a certain pressure and a certain volume, which are measured as P1 and V1, and then you change to a different pressure and a different volume, P2 and V2, you will find that the product of the first, P1 V1, is equal to the product of the second, P2 V2, and that is called Boyle's Law. The third experiment I'm going to do is also going to be done in a heat bath. I've got my container, and it's going to have a piston as before, but this time I'm just going to put one mass on it, and I'm not going to change it. So the pressure is always going to be the same. Right? The pressure acting down will always be the same. So when the piston doesn't move, it means the pressure of the gas is the same as the pressure of the weight, and that isn't going to change. So essentially the pressure here is constant. But what I am going to do is to change the temperature of the bath. So what I'm going to do, this is going to have volume markings down the side. The pressure isn't going to change, but the temperature is. So what I'm going to do is to measure, I'm going to change the temperature, maybe 20, 25, 30, 35, 40 degrees, and I'm going to measure the volume in each case. And what happens now is if I plot the graph of what I get, and now I'm going to plot volume against temperature, and remember it was constant pressure because that's not changing. Again, I'm going to get pretty much points on a straight line. As the temperature increases, the volume increases. In other words, as the temperature of the bath and therefore the temperature of the gas inside increases, it pushes the piston up and gives a greater volume. So this is a straight line, and once again if you extend it all the way back, now you are on a temperature scale, and guess what? That is minus 273 degrees centigrade, or 0 Kelvin. And what that says is that when you get to absolute zero, the gas has no volume. So at absolute zero the gas had no pressure, and at absolute zero the gas has no volume. And that gives rise to the formula that V1 over T1 equals V2 over T2. In other words, if you do the experiment at one temperature, T1, and you measure the corresponding volume V1, and then you change the temperature to T2, and you do the corresponding volume V2, then you will find that V1 over T1 equals V2 over T2, and that is known as Charles' law. And I remind you that the temperature must be on the Kelvin scale. So we've essentially found three formulae. We found the pressure law, which says that P1 over T1 equals P2 over T2 if the volume is constant. We found Boyle's law, which says that P1 V1 equals P2 V2 if the temperature is constant. And we found Charles' law, which says that V1 over T1 equals V2 over T2 if the pressure is constant. So three formulae, each of which has one variable constant. And you'll be delighted to know that you can combine all three into this formula, which is the general gas law, P1 V1 over T1 equals P2 V2 over T2. So if you have gas at a particular pressure, volume and temperature, and then you change it so that you get a new pressure, a new volume, a new temperature, then the pressure times the volume divided by the temperature of the first stage, will equal the pressure times the volume divided by the temperature of the second stage. Once again, temperature is measured in Kelvin. And in this circumstances, nothing has to remain constant. So now I'm going to do a series of exam questions just to illustrate how you might use this information. Here's the first question. I've got 6 times 10 to the 23 molecules, that's a lot of molecules, and it's in a container with a cross-sectional area of 0.4 meters squared. Each molecule exerts a force of 1 times 10 to the minus 19 newtons. So each molecule doesn't have much of a force, but there's rather a lot of them. What is the pressure? Well, remember that we define pressure as force over area. What is the force? The force is going to be the combined force of all the molecules. There are 6 times 10 to the 23 molecules, and each of them is exerting a force of 1 times 10 to the minus 19 newtons. So the total force is the number of molecules times the force associated with each molecule. And that's going to be divided by the cross-sectional area of the container, which we were told was 0.4 meters squared. So this is going to be, well, 10 to the 23 times 10 to the minus 19 is 10 to the 4. So we've got 6 times 10 to the 4 divided by 0.4. And that's going to equal 15 times 10 to the 4. And what is the unit of pressure? We're talking about pressure here. Unit of pressure is a Pascal. Or if you prefer, you can call that 150,000 pascals. Here's question 2. I've got 0.6 cubic meters, meter cubed, of a gas, and it's at constant pressure. But I cool it from 80 degrees Celsius to 20 degrees Celsius. What is the final volume? That was the volume when the gas was at 80 degrees. I cool it to 20 degrees, I keep the pressure constant. What's the volume? We need Charles' law. We need V1 over T1 equals V2 over T2 because the pressure is constant. Well, that's going to be the initial volume, which is 0.6, divided by the initial temperature, which is 80. No, it isn't, because it has to be in Kelvin, and for Kelvin you have to add 273, so it's 80 plus 273, is equal to the new volume, which we don't know because that's what we've got to try and find, divided by the new temperature, which is 20. No, it isn't. It's 20 plus 273. Well, that's, if you rearrange that, you find that V2 is equal to 0.6 times 20 plus 273, which is 293, divided by 80 plus 273, which is 553. And if you do that with your calculator, you should find that it comes to 0.5 meter cubed. In other words, it's a lower volume. It started at 0.6 meters cubed, it's now 0.5 meter cubed. Why? Because the temperature has come down. If the temperature comes down, the volume comes down. Here's my next question. I've got a fixed volume of gas. So obviously the volume is going to be constant. It starts at a pressure of 10 to the 5 Pascal, and I'm going to increase the pressure to 2 times 10 to the 5 Pascal. So it's an increase in pressure. The initial temperature was 25 degrees Celsius. What is the final temperature? That should be a question mark. What is the final temperature? Here we need the pressure law, which was P1 over T1 equals P2 over T2. What do we know? We know the initial pressure is 1 times 10 to the 5th. And we know the initial temperature is 25 Celsius, which means, of course, it's 25 plus 273 Kelvin. And that's going to equal P2, which we know is 2 times 10 to the 5th, divided by the new temperature, which we don't know. We'll call that T2. We need to be able to rearrange that equation, so T2 is now going to equal 2 times 10 to the 5 divided by 1 times 10 to the 5. Well, that's just going to be 2 over 1, which is 2, times 25 plus 273, which is 298. So T2 is equal to twice 298, which is 596 Kelvin. Remember, it's in degrees, sorry, it's in Kelvin, not degrees Kelvin, it's in Kelvin. If you want it in degrees centigrade, then you have to subtract 273, and that will give you 323 degrees centigrade. So look, we doubled the pressure from 1 times 10 to the 5th to 2 times 10 to the 5th, so it's doubled. We started at a reasonable temperature of 25 degrees Celsius, but look what's happened to the temperature. It's massively increased to 323 degrees Celsius just by doubling the pressure. Here's the fourth and final question which I'm going to do. I've got a container and it has 0.03 cubic meters of gas. It is at a pressure of 10 times 10 to the 5th Pascal, and its temperature is 5 degrees centigrade. I am going to release that gas into a new container which has 0.05 meter cubed volume. So the gas is now going to expand into a larger volume. And I'm going to change the temperature to 25 degrees Celsius. What I want to know is what will be the new pressure. Well, this is going to require the gas law because nothing is constant here. So let's start again. P1 V1 over T1 is going to equal P2 V2 over T2. That was the gas law. And now we just have to, well, what I think we'll do is we'll rearrange it to get what we want. What we want is, what is the pressure going to be? What is P2? So let's rearrange P2 to equal P1 V1 over T1 times T2 over V2. You've got to be able to rearrange this. P2 is equal to that lot, and then this goes upside down, as it were, T2 over V2. We know all of these, so it's just a question of substituting now. P1, you'll remember, was 10 times 10 to the 5th Pascal. So that's 10 times 10 to the 5th. Times V1, which was 0.03 meter cubed. Times T2, the second temperature was 25, but that's got to be converted into Kelvin. So that's going to be 25 plus 273. And that's going to be divided by T1, which was 5 degrees, but that's got to be converted into Kelvin, so that's 5 plus 273, times V2, and V2 was 0.05 meter cubed. And now all you've got to do is to get yourself a decent calculator. 25 plus 273 are going to be 298. 5 plus 273 is 278. So now you just get the calculator, and that comes to 0.64 times 10 to the 6th Pascal, or if you prefer, 6.4 times 10 to the 5 Pascal. So we started, if you remember, at a pressure of 10 times 10 to the 5 Pascal, and we've ended up with a pressure of 6.4. So the pressure has actually gone down. You'll notice that the volume increased, the temperature increased, the pressure has decreased.